Okay, welcome back everyone. In this video, we're going to talk about finally introduction to organic reaction. So far, we talked about that potential energy. It's something you have to care all the time, whatever you want to consider. So basically maximizing attraction between opposite charges and minimizing repulsion among the same charges can lower potential energy, which is favorable to have good amount of the changes. So by repelling and attracting, you basically change distance or the angle. That's the component for structure. So in changing structure, you change the distance or angle between electron pairs, or even between positive charges and negative charges, whether they are from internal nuclei, or between atoms, or the functional groups, or even molecules. So also one other thing was size. The size of the atom, or even size of the overall structure with a long chain can change if there is an internal interaction, and then they will have a different conformation, so they can change the size. That also has to do with the structure. So increasing internal charge of an atom can change the size of the atom. Also, amount of the electron you inject by chemical reaction, it can also change the size of the atom. So the amount of charge is important, but also when you compare different atoms, how many shells you have is another factor that changes the size. But not only the size, some properties. Of course, size and angle between bonds if you are dealing with the molecules. But more importantly, the electronegativity change if you have a bigger shell or smaller shell atom, or a neutral amount of electron or positive negative amount of electrons. And then you can imagine the electron affinity change due to the size of the shell, because bigger shell can accommodate more number of electrons. So some atom has better potential to be negative than the smaller ones. So once we completely understand the structure and their property of the atom, yes, you are always requested to understand when you bring two atoms together, their even distribution of electron get disturbed, and you bring more electron in the middle, and that's sigma bond. First, two electron. The additional electron brought into the middle will turn into pi bonds using p orbitals or d orbitals. And when you form bonds, the more electronegative atom determined by effective nucleus charge and the distance that's coming from the size will determine the polarity, the partial charges. When this is more electronegative, for example, electrons spend more time not only in the middle area, defoliated from the side area, but spending more time on, the more electronegative atom's shell. So that makes more electron rich, so partially negative because electrons are negative, right? So that gives you polarity based on electronegativity. But also, we talked about it, that the polarity and the electronegativity can give you an idea about bond dissociation energy. The atoms that are relatively small on the periodic table, they bring electron closer to their nuclei, thus it can hold electron better with a greater electronegativity. And when you form bond using those atoms, the electron in the bonding area will be obviously more attracted and get stabilized. So you tend to have a greater bond dissociation energy. Another fact about the bond dissociation energy is that when you have different size of the two atoms, say you have about same electronegativity, but one is big and small versus both have about the same size, then by some quantum region, this case with a similar size tend to have a better overlap between the orbital and able to create a stronger bond, having greater bond dissociation energy. So molecule like H and Cl will have a weaker bond and easier to break. So that kind of property is basically coming from the detailed structure of atom and understanding their potential energies. Once you understand that, when you have a reaction or any chemistry going on, you have a more than one molecule in the solution, so you can think about intermolecular interaction. So that can be applied to the various things. This can be applied to the solvation, which means the solubility kind of mixing energy. As well as the physical properties like a melting point, boiling point, etc. Furthermore, when molecules have some interactions, they can further go and break a bond and form new bond, and that's going to be a chemical reaction. So this chemical change is the main property that we are going to focus on in this video afterwards as well. Chemical reaction. So that chemical reactivity is related to how stable the new bond is, how unstable the old bond was, as well as how stable is the other product. and that is our main focus on in this video. In addition to this, organic chemicals, as you have studied, have multiple bonds. So say there's a central atom with a multiple bonds, 3, 4 multiple bonds, and these bonds consist of electron, and they are constantly pushing each other to minimize repulsion. So as soon as you lose a bond, the geometry get readjusted and change the whole structure. Thus it changes the property as well as the energy. So there are cases you have to know that this is favorable, or this becomes more unstable, depends on situation. Also, carbon is expert in making multiple bonds like this, but then automatically you should know whether this all anti structure is more stable, or this eclipsed one's more stable, or this gauche form is more unstable. It all depends on what type of groups you have in the molecule. If there are situations like these X and Y's have opposite charges, then they like to come close. But eclipse is not favorable most of the time, but you can force them to be in the eclipse, so you never know. So before you apply these fundamental properties to predict the chemical reaction, for organic reactions you have to find out the details of the equilibrium you might have between different structures, especially conformations. So from now on, I will talk about what conformation of the organic molecule you have in most abundant, as well as which one is the more stable one. The more stable one is more abundant, but it's not always connecting to the major reaction. Sometimes it's the less stable conformation that gives the major product. So the effect of the complex phenomenon of conformation or other geometry is the main factor of organic reaction. And obviously, as we discussed before, temperature allow the chemicals to explore all the possible chances, so temperature is another main factor. Then, like we discussed earlier, the bond dissociation energy is a main factor. Then electron affinity to accept the electron as a product or as the reactant becomes a major factor. And what type of solvent you're using can change the reaction course greatly, because solvent is the one stabilizing or destabilizing chemicals. So in considering many factors, there are other things that you always have to keep in your mind, which is what are the typical reaction type. To learn complex reactions that doesn't have any typical type, you always have to start understanding and using the typical reactions first. Then, using these typical reactions, you need to know there are always a multiple path you have to consider before you finalize that one of them is your main or minor. Also, there are cases where you have the reaction goes on in multiple steps. The reaction doesn't stop after one step of reaction. So please keep this in mind. Then we'll start talking about reactions with a simple example first. There are various different kind of reactions caused by different intermediate or different reagent or kind of conditions we give. You can cause reaction by breaking bond homolytically and create radical intermediate. Okay, so we're going to talk about this later in detail, how to cause this. And there are cases you can initiate the reaction by creating ions. Or there are type of reaction you can do using, pi bonds. So it's neither radical or ionic. So pi bond and so on. So the first reaction we're going to focus on is the ionic reaction. Then soon we'll be talking about radical reaction. Later on, the pi bond reactions. So this ionic reaction we are going to focus on is when you have these positive or negative ions that's normally formed by heterolytic cleavage. For example, both electrons either stepwise or concertedly give electron to one side of the bond, and the side getting two electrons become negative, the other side becomes positive, because in the bonding one belongs to each side, but two taken by one, so this side end up losing, so positive, this side getting electron, so negative. So let's take a simple example from general chemistry and start our discussion about ionic reactions. There. Making sure you see the paper clearly. This is HCl, hydrogen chloride. You know it already, this is acidic and OH minus is basic. But when you do organic chemistry, it is not always obvious which one is acid, which one is a base. So you'll have some training later on to see how do you choose your base. If there are more than one potential base, which one do you use to choose to react? Same for the acid. How do you know which one's acid, and how do you go with it to form a new product? So when you notice OH, first thing you have to remember is, you need to do some changes if you can. If you cannot, then this is it. They stay like this and there's no reaction. So what do you mean by if you want to do something? Well, can you lower the potential energy by rearranging electron as well as atom? Because if electron goes, then the atom comes with it. So the potential energy needs to be lowered if anything's going to happen. Then when you look at the OH, when you consider Lewis structures in all the previous lessons, the oxygen is the one that has a negative charge, because oxygen has total 8, but its own 7 electron, not 6, so negative. Here you see easily applying electronegativity in induction, chlorine becomes partially negative. Then, which electron pair is the most unstable electron pair? That's what you need to find out. Knowing this whole thing is base or acid by memory is not going to work in the future organic material. So pretend that you don't know, you did not memorize this as a base and acid. The question is, how would you figure that out? There are 3 acid-base concepts in acid-base reactions you have learned. Arrhenius, as a H plus donor acid, OH minus donor as a base, and Bransted and Lowry, the H plus donor acid, H plus acceptor as a base. But most broad and the latest definition is Lewis definition, using and focusing the electron pair. So among OH, it's the oxygen that has repulsion going on, unstable. So it's one of the lone pair or sigma electron. But sigma electrons are more stable, so it must be one of those 3. What about chlorine? You say they are also repelled with a partial negative. Yes, but first of all, it is partially negative. Second of all, the chlorine has a big shell, so the repulsion is not as bad. So, lone pair on the oxygen is a better electron donor. So, it's not just OH base, but in doing organic, you need to know it's this lone pair N, not the sigma bond. It's the base. Try to donate away the repelled electron. Then in the acid, you gotta have an atom with an orbital that's possibly accommodating electron the best. In this case, it's just a hydrogen, right? There's no other attractive atom. Although warning is that it's not always the partially positive atom that is receiving electron, because the electron in the molecule keeps moving around, and when a greatly negative ions approach the molecule, then they can actually push electron away from where they are and induce opposite charge in the other side of the molecule. But for now, let's continue by giving electron to the partially positive hydrogen. Then you should know the hydrogen has a small shell that can accommodate only maximum 2, and there you are, you have 2 electrons sharing the shell of hydrogen. And these are also in the chlorine shell. So that electron comes to the hydrogen, a little bit of attraction. Then the electron is attracted by +1 from the nuclei. So then they say, oh, is oxygen too much electronegative compared to hydrogen in order to form ionic bond? Then you know, answer is no. So you know the electron will be shared, although electron like to spend more time around the more electronegative oxygen. But partial electrons given to the shell, that means these electrons are repelled away. So they don't stay here, they move to the side. The electron is running around the third shell of the chlorine, and they're just shifting around along with the other 3 pairs in their respective orbitals, you know, sp3 hybridized orbitals. So you have 2 arrows. An arrow from the lone pair of the base to the acid hydrogen. Then the bond in the acid is broken and given to the chlorine, and chlorine was neutral with a slight excessive electron, partial negative, but now you're gaining total 1. One of them was a chlorines, but the other one is pushed away from hydrogen due to the given electron from unstable oxygen. So the electron is moving to the chlorine. That's when you approach the transition state. So the transition state is not like a quantum state. You jump from the ground state to the transition state. It's a gradual change because electron density gradually moving from oxygen to the hydrogen, then hydrogen chlorine bond to the chlorine. So as you come close, you break bond here. So when you have a partial broken bond here, partial formed bond there, and you have their transition state, which we'll talk about later. Say gradually you completely transfer the both of the electron in the sigma bond between hydrogen and oxygen. That means you completely push them out. Then you could form the chlorine free from hydrogen, having one more electron, so negative charge from neutral, gaining electron. And the hydrogen shares electron here, so you have hydrogen bound to the oxygen by sharing electron, leaving other 2 electron pair on the oxygen, and then oxygen gave away 1 electron. Although they're sharing, you know, 2, both were oxygen's electron, but in the bonding, one only is oxygen's, the other given away to the hydrogen. So it's the same as oxygen lost 1 electron, so -1 losing electron became neutral. Formal charge is neutral. However, it has a partial negative charge because both compete the electron, and the electron like to spend time on the oxygen. So, you know, the judgment actually can happen during the transition state. If this is more better stable you know, form for the electron, getting more attraction, less repulsion compared to the before, then the transition state happens quickly, meaning they start to get stabilized and turn into this. If this was unstable, less stable than this, then in order to reach the transition state, you have to give a lot of energy, and they have to get really close and give a lot of electron transfer to the acid molecule. Yet, you're not going to form stable one, so they will eventually have to come back more to this way than going to that way. Let's see whether it is the case. First, you want to consider bond dissociation energy. So from your general chemistry, you learned that reaction includes bond break and bond formation here. So if you know the bond dissociation energy of this and this, from then you can calculate the heat of formation. If the heat of formation is negative, which is exothermic, so the reaction is favorable, and if the value is positive, meaning you gain the energy, you absorb energy, so it is endothermic, so it will be not favorable because the general curve for the potential energy will be exothermic this way, favorable, losing because it's losing energy, but the other way it's going to be endothermic. Sorry about that. It's not going to be favorable. So it becomes important to know whether relatively the product is more stable than the reactant or less stable than the reactant. And the bond dissociation energy is supposed to give you an idea about that. So by the definition, bond dissociation energy is the energy requires to break a bond. But when you form, the same amount of the energy come out, because sharing electron forming bond makes the electrons more stable. So same amount of energy, when you form bond, it comes out, becomes more stable. When you break a bond, you bring the electron in the bonding to the non-bonding, so you need energy. So it's not favorable. Electron like to be shared with more attraction from both atoms. So when you remember, if you remember what I said, the chlorine is big, hydrogen is small, and oxygen is smaller than chlorine, and there is a hydrogen. So the size difference is, here small, but they have a big size difference. So that makes already this bond weak. Second, electronegativity of oxygen is greater and small size, so the shared electrons are close to the positive charge. So they have a stronger attraction, more stable bond, and while the chlorine has a big shell, the electrons are away from the +7 after shielding. The electrons are not as attracted, so the bond is weaker. So this has a more bond dissociation energy, but you are forming this bond, so you don't need energy. Energy is coming out, more energy is coming out because this is more stable. And this is weaker bond, so breaking it takes less energy. So the energy that comes out here is enough to break this bond, so the reaction is favorable. It sounds okay, right? However, there's a mistake here. First, bond dissociation energy is actually when you break bond homolytically how much energy it takes. But there you don't break bond or form bond homolytically, so you cannot use this. Two, the homolytic cleavage make the product neutral, but if you do heterolytic cleavage, you are making either positive or negative, like I showed you in previous slide. So those ions have a more significant effect by solvent. So solvation energy is excluded. That's why using bond dissociation energy never successfully predict organic reactions, especially. And also the bond dissociation energy given in the table is mostly for gas. But plenty of, actually majority of the reaction, organic reaction, takes place in the solution. So that also is another factor for mistake. Then you may say, okay, we have electron affinity. They can solve the problem. Affinity, they can solve the problem because electron affinity by the definition is when you have neutral atom, you give electron and you make a negative ion, then how much heat is coming out. Basically meaning how well this neutral atom is accommodating additional electron and gets stabilized. So there, like I said earlier, the size becomes important. If you have a bigger atoms, they have less chance to get repelled among the electron in the negative condition, so they are more stable with a minimum repulsion. If you remember, the bond dissociation energy has to do with electronegativity and the size. So let me comment on the effect of the bond dissociation energy and the electron affinity. In this particular case, the bond dissociation energy between HCl and the HO involved in bond break and formation in the chemical reaction is the H and oxygen forms slightly more stable bond by less than 10 kilocalorie per mole. However, there's the main factor that's been ignored. That is the main factor for most of the ionic organic reactions, which is chlorine has much greater electron affinity to be negative compared to the oxygen, small oxygen. That's more than 50 kilocalorie per mole. So if you only consider bond dissociation energy, sometimes you get the opposite prediction. So I'll ask you to first pay attention to the ions. See which one has a better ability of accommodating extra electron to lower the repulsions or provide more attraction. So in that context, something that helps electron affinity for anion is resonance. In general, if you have a resonance ability, you can delocalize and spread the electron so you over the bigger functional groups rather than one atom. Therefore, it's the same effect as having bigger shell. You are lowering repulsion, so you're stabilizing electron by reducing repulsion, just like the chlorine versus oxygen. Also, if you spread electron over few atoms in resonance, those atoms participated in resonance will provide their nucleus charge to attract more the electron. So many times resonance is more effective way of stabilizing the ions compared to size, and most of the time it's better than just electronegativity. Next factor I want to talk about is solvation. Most of the time the reaction takes place in solution, I said. So what solvent you use is very important. If you use a polar solvent that can stabilize these anions, then the energy of the anion will change greatly. If you use the solvent that destabilize the anions, then you can increase their energy, and that changes the relative energy greatly. So what type of solvent you're using, you have to pay attention. Not only anion, but these polar and the less but still polar, or sometimes non-polar compounds you have, they have also like sort of solvation energy. We can call that also as a mixing or solubility. They can also, stabilize or destabilize product and reactants in the reaction. Next factor could have been whether you form solid or gas. If you form solid, that means the anions are attracted by cations, and they are more stable that way rather than dissolved in solution, meaning the solvation is not as good and solubility is not as good, so they precipitate out as a solid. That has implications such as you don't have those solids in the reaction anymore. For example, if the Cl- came out of the solution, there's no more chlorine available except the surface of the solid, which is a small portion of the all. That means it has a less chance to go back, because even the product is going to keep reacting and try to go back. Gas is the same. If you form gas, it disappears from solution or present in low concentration, so the probability for a reaction is less, because for reaction they must present and make a collision. Next factor is something we talked about in the very beginning of the series of the video: temperature. Temperature is given to the all chemicals. So the temperature is allowing them to have a high enough kinetic energy so they can go over activation energy, like this for the exothermic, or for this much for endothermic. And as you can see, the endothermic reaction has a higher activation energy than the exothermic. And also, the transition state happens quicker and start to get stabilized quicker for the exothermic. For endothermic, you need to bring the two reactants very close, and yet when it starts to go down in energy to be new product, if the product is not as stable in the endothermic, then it's not gonna form as much because it will go back more. And that's called the Hammond postulate. So we get some idea about the transition state using Hammond postulate, depending on whether the reaction is endothermic or exothermic. And how do you know something is endo and exothermic? Like we've been talking about, whether the product is more stable than the reactant or less stable than the reactant. I know it's repetitive, but it's so important, So I have to say, how do you know the product is more stable than the reactant? You have to see first electron affinity for the ions. So if you have ions, then you give your attention to the size. Then see you have a resonance. Then you give your attention to the newly formed bond, whether they are more stable than the bond you broke. Then you give your attention to the solvation, and so on. So when you have more than one possible reaction path, which one you're gonna be? You're gonna have main product. That also comes from the more careful consideration of the temperature when you have a good idea of the energy surface. Okay, let's try a new example. If you have seen this before and you know the answer, you can solve it, what the product might be. However, if you don't know this example and you never seen before and you don't know how to analyze, then you have no answer. But unfortunately, in organic reaction, there are so many variations, and it's so easy to make the prediction completely opposite by changing and tweaking structure a little bit or factors just by a little bit. So I highly recommend not to memorize again, but try to analyze and apply instead of memorizing. So the mistakes people can make is this: oh, I have like hydroxide, I have a negative, instead of using lone pair after considering which electron is most unstable. So the unstable electron must lose electron concept. Instead, you want to say, oh, there is a base, very strong base, and I have a hydrogen, so let's give electron. And then the electron in the bond, just like here, goes to the shell of the other atom in the bond, so it's boron. Then you can say, oh, I have one less hydrogen on the boron, and the boron received the electron, so it's a negative charge, just like the cone. So you think this is application. And NH2 gained one more hydrogen, so it's 3, and given away electron, so it's neutral. Perfect. But that's not right. After studying this example, if you memorize few things, then you again will think, oh, I can now apply to the similar example. And my advice is, please drop that type of a strategy. It's not going to work. So when we work with a simple example, I want you to build up the skill of thinking. So first thing I said you should do is based on the potential energy concept, I want you to analyze the structure in order to deduce any properties relevant to the reactions. See these properties. Before we start studying about typical type of reaction, you need to use these simple examples I'm giving you, mostly coming from your general chemistry, to learn how to apply these fundamental factors to analyze the reaction before we have a complex organic conformational issues or some other issues down there. So what we should do is, nitrogen is a negative, so it must have 6 electrons, and maximum is 8. So 1, 2, 3, 4, 5, 6. That's it. So nitrogen has a 2 lone pairs, and the 2 hydrogens are in sp3 s orbital kind of bonding situation. So it's not the negative sign that's given away, but it's the electron. So your base is not anymore the OH or NH2 minus, or not even a negative sign, but it is the lone pair, not the sigma electron. So the lone pair is going to be given to one of these atoms. So the base is pair of electron in ionic bond, and acid is an atom, empty orbital of atom, but okay for now, atom. Then you have a boron having 3 minimum attachment to the 3 hydrogens, and from the periodic table you memorize, you should know boron has 3, and that's neutral, and that's it. So, this is a second shell element, you should realize, and you have second shell has sp orbitals, and you are using only 3 of them, so sp2 hybridized, meaning you have empty p orbitals perpendicular to these 3 lines. So here you have an empty p orbitals, which is this guy, and it can have up to 8 electrons. So when this gives an electron to one of these, you should know first the polarity of them. So partial positive, partial negative. Is it correct? Not really. Actually, hydrogen is more electronegative than the boron. So here you have to know some of the common electronegativities. So hydrogen is negative, boron is positive. It's perfect. Boron is positive, it's negative, and boron has empty p orbital. So what's happening next? One of the lone pair, the base, is going to be given away to the boron. You don't have to break a bond in this case, because the boron has only 2, 4, 6 electrons, and it can have up to 8 electrons. 2 more comes and it's fine. Because breaking bond is energy requiring, so meaning the compound must absorb energy to do so, and meaning the reaction becomes endothermic. You don't want to do that. Sharing electron lowers the energy of the lone pairs in the negative nitrogen. So that's perfect. So the nitrogen comes this way, and the boron is flat. I hope you see how I see the molecule prospectively. So the empty p orbital receives the negative electron to it. Then as these electrons come to the boron, these guys are pushed away because the electrons repel, these repel to these guys. And after forming bond, one of the electron will belong to the nitrogen, the other to the boron, so nitrogen losing electron. So you still have this sp3 lone pair, sp3 with a hydrogen s bond, sigma bond, another one behind. Then this is a new bond you just formed, and the boron is making this sigma bond using the sp3 with the not P anymore, sp3 with the new sp3. Why is it sp3? Because you have 1, 2 pairs in the bond, third and the fourth in the bond. So sp3 of nitrogen, sp3 of the boron forms the sigma bond. And this bond changed, right? Here the sigma bond was sp2 and S of the hydrogen. Now this bond got weaker, sp3 with the S. sp3 having more P, unstable orbital character, compared to the sp2 with a more S character. So, you know, more S character means more stable for electron. So this electron pair was more stable, but now less stable, since boron received a lot of electron and changing the angle. So the nitrogen loose electron became neutral, but boron from the neutral 3 electron state receives 1 electron, so this becomes negative. You immediately notice that there is eclipsed. So this transition state and the product is not the best. So you have rotation around the single bond. You're going to have a staggered product. So my aim of this video was to change your mindset from you know, just fragmented concepts understood and then memorize and try to deduce to solve problems. Rather, I want you to understand and connect and inductively apply through the analysis, and without using any generalized type. Freely you approach the given compounds to come up with the right prediction. So this is a part 1 of the intro to the organic reaction. I'll continue after this. Until then, have a good day.